Thanks for the very kind introduction, Dhruv, and I'm very happy to be presenting first as part of your pre-conference workshop series, and really excited that such an initiative is happening in India. And my entire volunteering initiatives have been around this idea of building capacity at a national level across various uh, channels like GDG, be it ANRF, be it Dhyuti, and even at my alma mater, IIT-Madras. And so here's a quick overview of what we have built, which is Dhyutiman PI. PI stands for Physics Informed. So I'll go give a quick overview of what Physics Informed Neural Network is as we move forward. But what Dhyutiman PI is a skill-based agentic framework for physics-informed neural network research and how we can automate it and scale it. But here's the agenda for today's session. So I'll start with what the problem was, what the motivation behind Dhyutiman PI has been, and what are the 4 agents that help achieve what Dhyutiman PI does, and what are typical modes, guardrails, and what are some examples that we can look at which are verifiable, and some workflows that we can adopt using Dhyutiman PI, and where you can run it, not just on Claude Code or Claude AI, but also Cursor, Antigravity compatibility is also baked in, and what are the next discussions and next steps, and some recommended open problems that you can take up if interested. So it started with the larger question around close to my thesis submission was, can I have agents reproduce my thesis? Number 1. 2, can my thesis become a living, evolving body of work? Why should the research in a particular topic through me or through people who carry forward work not just be restricted to that particular thesis, but rather move forward, be able to build on top of it and automate some parts of it? And why shouldn't a thesis that's a body of work that's been evolving over 5 years, why shouldn't it evolve further? 1, and how can it also become textbook material, right? So adding to new knowledge base, and you get to build on top and also scale it and scale its impact. That was a larger question. So then digging further, so here's a QR code of my thesis if you're interested to go further and read a bit more on what I've worked on. This is a good way to go check it out. And I have a podcast around it. I have a very popular science styled presentation as well. So you also have a complete notebook LM that you can go through. And the large 4 questions were, why should the thesis not evolve as new knowledge adds? How do I scale such evolution? How do I automate such work with AI? And what methodology guardrails should I adopt, given that I have some expertise in data-driven and physics-informed deep learning? These were the large guiding questions. Now, a quick overview of what physics-informed neural network is, which is pretty much the major meat of my thesis, was physics-informed neural network is nothing but a simple neural network backbone that maps different kinds of input features, such as your system parameters, system in the sense of physical system that is governed by certain laws of physics, and the spatial coordinates where it operates, or temporal coordinates where it operates, and then additional control input for that particular physical system. These go in and get mapped to your target variables, and then there are data losses and physics losses that are constructed, and a weighted combination of this is your total loss, which gets optimized using a gradient descent based optimizer. Now, what the data loss penalizes is any sort of observation simulation data on the target variables and additional data constraints such as boundary conditions, initial conditions, if you're aware of what partial differential equations or ordinary differential equations are. And then you have the physics loss, which embed these governing equations and known physics, which could be partial or complete knowledge of the physics, into the loss function through least squares residuals. And then a weighted combination of this is what is used to further optimize and train your model. Here is a look at the standard research methodology when there is only an average human researcher involved, right? So he starts with a literature survey. There's a vague idea in head. And then as he or she assimilates the knowledge that comes out of this literature survey, they get into problem specification, hypothesis, design of experiments. And it can so happen here, although it is shown linearly here, the problem specification can also happen before the literature survey. and then you're looking at a hypothesis, and then you try to see if people have already done that. So it can also be an iterative process, but let's assume that it's currently linear. You start with literature survey, you have some existing knowledge, and then from there you build on some problem specification, hypothesis, you plan your experiments that you would like to run and design what your candidates are going to be for your experimentation. Like it could be an MLP, it could be a CNN, it could be a transformer, etc. And then you start implementing or building a scaffold of this model, data, modules, etc. And then get into experimentation, then run your experiments, log your experiments, and analysis and reporting. Then based on what you identify, you update your belief or hypothesis. And this is how it is, right? So now this is again an iterative process. And often you have informal handoffs from each stage where you don't have all of them integrated in one place. So literature survey, problem framing, code development, all of them live across different modes and not often integrated, and sometimes not reusable across labs. And sometimes you're often too celebratory early on when you find some results that satisfies your hypothesis, but you're not looking at counter hypothesis and say, okay, what if it was false? What other experiments or dimensions or axes am I missing in my study? And sometimes this is also very slow. It's not easy to scale. And then sometimes if the junior researchers often reinvent practices of every new problem, and the way a particular researcher does implement certain things on his problem or her problem changes to another researcher. So there's no standardization as such, right? And research methodology itself is attributed to be a bit creative, and people have their own aesthetics or cosmetics to it. However, what do we do if we were to bring in agents here? So the first and foremost thing is we need some sort of standardization, and we need to have a way to integrate exchange between each and every step of this workflow and be able to consolidate the findings across each and every step. And this is where we have 4 agents. One is a surveyor, which takes care of literature survey, framework, which takes care of problem specification, hypothesis, and design of experiments. Then we have an implementer, which scaffolds the code, sets up experiments. Then you finally have an analyst, which looks at the results and also identifies what could have gone wrong. Right now, it's easy to set up all these 4 agents. Let me just say that. But what's difficult is to figure out what potential edge cases might arise in each of these steps of your workflow. And typically, PIN literature has very wide, inconsistent terminologies. So I might say that it's a failure-informed sampling. Someone might say it is residual-informed sampling. Some might say it is spatially adaptive sampling. But underlying all these methods might be somewhat similar. Now, and each one of them might claim that they have come up with this idea first. So how do you disambiguate? How do you ensure that you consolidate all of them, assimilate, and make sense of these methods and look at a unified abstraction? Now, this is where a lot of guardrails come into play. And so firstly, the literature survey agent ensures that you look at it creates a specific knowledge base, and it ensures that a taxonomy of variants are accounted for in the skill itself. So it searches across a different axes, like training tricks, variants, failure modes, and what is operational and not encyclopedic, or the medium articles do not cut in. Right? Blog posts do not cut in. It's mostly heavily based on multiple sources of the journals and conference papers. That becomes a constraint and criteria. And then the other important thing about framing a hypothesis is the hypothesis should be falsifiable or verifiable. It is to say that, can I quantify the outcomes of a particular experiment, and can I link it back to my hypothesis, right? Rather than saying that, okay, PIN might work well on 2D heat conduction, rather than saying that, if I were to say, PINs work well on 2D heat conduction if my relative error is below a particular order of accuracy, right? So if that is, these are ways in which I can frame the hypothesis. And the other important aspect is you need, let's say if I were to say, give a very vague query, solve heat conduction using PINs. The next question is to ask, what are the different variants out there? Can I get back to literature survey? Or just expand the query further and look at what goes into solving 2D heat conduction using pins, right? So you need to expand the query further. We'll look into the skills in detail to understand what that means. And the next is to set up scaffolds using, at this moment, I have kept it very simple at linking it only with NumPy, PyTorch, and a very basic physics information learning library called DeepXDE. And you can choose to implement across any of these modalities. And it also has a verification harness such that it compares against this reference solution. So reference solution also becomes very important when you're using auto research in the context of pins. Without reference solution, you cannot confidently claim that pins work. Because firstly, in many cases, pins are used to solve a PDE, solve an ODE. So unless you have a reference solution for that system, it becomes very difficult to verify whether your methods even work. Or does it just produce junk solutions? And finally, analysis. So when you do analysis, you should always analyze as a reviewer so that you maintain objectivity and are not biased towards your own experiments. So this was also baked into the analyst's skill set. Now, this is what the workflow for Dhyutiman Pi looks like. So again, of course, many parts of this can be iterative. You need not move to the next step in a linear fashion as shown here. We can discuss that sometime. But here is where you start with literature survey pin. You have a pin problem specification skill. Then you have a pin scaffolding skill. You have a pin analysis and reporting skill. And then you update your belief. And again, modify your specification. Or if you're happy with what the report looks like, you stop there and you're done, right? So now I think it'll be a good time to look at what these skills look like. So we have 4 skills: literature survey pin, pin problem spec, and pin scaffold, and pin analysis report. Yeah. So this is the repo. I hope everyone's able to access the framework.
Yes, I've just dropped the link. Yeah, so they should be able to open it.
Yeah. Yeah. So the interesting thing about, thanks Dhruv for also mentioning this in the chat. So the interesting thing about this is a lot of the guardrails that I mentioned now are applicable to any scientific problem where you know that you could verify the solutions that come out of your experiments, right? So as long as you have a framing in a way that your hypothesis is falsifiable or verifiable quantitatively, you're good to go. So you could adapt the skills. You could take the help of Claude again, adapt this not just to pins. Let's say you want to look at medical imaging. You could look at that, provided you have good data benchmarks for that. Yeah. So now let's look at some of these skills, so starting with literature survey. So I will actually focus on a couple of places here in a skill. I think you can go through it on your own as well. But when to use the skill had been very important, in my opinion. And also the other important part was the sources to research and query expansion being a very important part of this skill, because if you don't have query expansion, this could also be attributed to a failure mode, right? So the fact that if you don't let it search or give enough access as a domain expert, if you cannot give it dimensions or directions in which the agent has to search across wide and deep, it becomes impossible for the agent to really make sense of what to gather information from. And this happened to be a failure mode initially. So the clear difference you would see is, I would suggest people to try it out themselves. Remove this query expansion section from the skill, load it on Claude, run a literature survey on pins to solve heat conduction, see what it gives you, and then give this. And of course, there's one catch here. So in the PDEs, you see ... and a bracket. So you could have a similar ... and a bracket. So it knows that it has to search beyond these variants as well. But interestingly, Opus is very intelligent. It figures out that, okay, it has to search across these axes. And this becomes very important. So as a domain expertise kicks in, so you need to bake these dimensions along which you need to search literature and get assimilated information and then pass it on to get better at your problem specification. And then there's a format in which your knowledge base should look like and what the workflow is. and so on, right? And so there are other important part is your anti-pattern. So exactly, right? It has to be actionable. So what to try, what not to try, what exists is not important. What to try, what not to try. Recommendations become very important. And looking at, okay, so here I kept very specific to pins. There's another class of models called neural operators. I can always modify this to say that no, I also want neural operators. But here the scope becomes very important to say that, okay, I'm looking at only pin-based research. So it's just pins, I'm not looking at neural operators, which is a separate class of networks. If I want to modify, I can modify. So anti-patterns also become important. So coming back, so for literature survey to make it really effective, know when to use the skill, and when you have to bake this in, and ensure that you target those sources to search that you always have searched and something that you might have also missed out on. And for example, author group pages, like following very top authors in this area, highly cited folks like Kanyadakis, Perdikaris, his collaborators, Steve Brunton, Nathan Kutz, etc., and the contributors for various modules like DeepXD, Modulus, etc. And then query expansion, and then anti-patterns. So these become very important for this particular skill. And I'll even show an example if time permits to see what happens when you don't do literature survey versus do literature survey. And then let's look at problem spec. This is where it turns, the idea of the skill is to turn your vague statement saying that I want to solve heat conduction, and turns that into a very well-posed problem, which can be translated into a pin code or a training problem, right? That becomes important. And let's say if I want to solve heat conduction with a pin, it has to be machine readable. It should be mathematically well framed with what are the governing equations. If I were to train a physics-informed neural network, I need a governing equation in place. So what is that? It has to pick that up. Are there literature survey notes already? So what's interesting is that all these agents look for an upstream artifact. So problem specification skill looks for an upstream artifact that has been generated with the help of literature survey pin. And similarly, problem scaffold looks for an upstream artifact which has been generated from the problem specification, the hypothesis, design of experiments, markdown file that comes out, or even a JSON object. You can configure it based on your requirement. Then you have an analysis and report, which looks on what runs have been carried out, what was the problem spec, and so on. So upstream artifacts also determine how the downstream skills behave. So the interesting part is you don't always have to start with literature survey. You can enter at any point in this workflow. And the other key message is you don't have to only do one Dhyuti Pi workflow at a time. You can do multiple Dhyuti Pi workflows and at different entry points as well. So you have a clear literature survey. Maybe the user is unclear about a PDE setup, which is where the knowledge mining part comes and helps it. And this skill helps you frame it better, and you can verify it. Then you look at problem statement, governing equations. This is typically how we frame a problem. Even if you look at any pin paper, this is how we would frame a problem. You have a problem statement, governing equation, what are the domain and boundary initial conditions, reference and ground truth. Do I have any reference solutions? And mandatory reference solutions has been baked in, so you have a way to validate and verify the outputs of your model. And then architecture and your training plan, what are the hypotheses, falsifiable. It has to be phrased such that there's more causation involved. So changing something results in something else, right? So that causation has to be picked up by these hypotheses. So I suggest that whenever you create a skill, I think Sachin has also pointed out very nicely that these skills often have rough edges if you create it in haste. So once you create, look at them in detail and try to iterate over a particular skill before you move further. And you can also do an A/B testing on your skill, like what happens when you change some part of your skill and your instructions as you move forward. And also, so it's important when you look at problem specification, it's also important what is out of scope, what are your assumptions. So it's typically a mathematical problem framing that you go look at. What are my assumptions? What are my governing equations? How well posed it is? What makes it well posed is often my assumptions and what's out of scope. and what I want to implement, what are my candidate functions that I need to look at, and what are the success criteria. And then the workflow is pretty straightforward to look at, and then you can choose any particular model that you want to work on. So I have taken 2D heat conduction as an example here, given the time constraints. But the larger goal for me was to build this so I can actually evolve and further improve on my thesis work already, which was on unsteady flows, Navier-Stokes fluid dynamics problem, and that to a past of moving body. The goal was to probably simulate flow past flapping wing flyers like birds and insects, right? So that was the larger goal, and see if I can do this with these agents. And that's how it started, but example would be a 2D heat conduction. Again, anti-patterns, specifying something without a reference, cannot help. I mean, ideally, you want to prevent it from hallucinating. You want it to pick up things from given literature, and then frame certain additional modifications and reason out on them. Okay. So this again comes from domain expertise. That since I worked on pins, I know that you have it's a multi-loss or multi-objective problem that you're multitask learning problem that you're trying to solve with pins, because you have too many loss components to optimize and balance. And how do you balance that is also another issue. So you cannot treat your loss weights as fixed, rather see if you can modify that also in your ablations. Okay, so this is an interesting question by Alok, which says people often struggle with models collapsing to non-novel approaches during auto research runs. Could be because of literature survey and problem specification. So if you have assimilated your literature survey well, then are we okay? This is not based on auto research; it's completely skills based. So if you have your literature knowledge base well defined, and then look at open problems that have been posed by the literature, what are the gaps? If you can identify the gaps in the literature, then ensure that your problem specification and hypothesis depend extremely well on these gaps, address these gaps, and also look at a baseline, which is probably the non-novel approach. And then any improvement is basically a delta on this. And that is one way to force your agents to look at those kind of modifications and ablations in your model. And then I'll walk you through the pin scaffold. I think the pin scaffold is relative. I mean, I spent a lot of time on the literature survey and problem specification because that becomes very important when you have to solve problems in pins, and framing is the entire masala for your getting the right outcome from your research itself. Scaffolding is about, okay, once I have these, I have seen that Claude is really good, be it Sonnet or even Opus, they're very good at getting the code out. And I think here I was a bit hand wavy, to be honest. I just wanted it to do a very basic scaffolding in PyTorch, NumPy, and sometimes even look at if I can get them easy to borrow functions from DeepXD, which is another module for scientific machine learning, specifically pins. You can also borrow some of those functions and run. And the output structure was important. And what I need to verify, again, becomes important. So I have a model script, I have a problem script, which translates the problem framing into the entire set of functions such as physics laws, etc. I'll show that in a bit. And you look at training script, verification script, your errors, reference solutions, plots, etc. Then you look at the run script, just traditional ML code-based structure. And then you have your checkpoints, logs, verification. And then once you have these outputs become your artifacts to be handed off over to the analysis and report. Yeah. So, however, there are a couple of failure modes in pins which we need to avoid. So, which specifically comes towards implementation. And one is in terms of the sampling of boundary points. I don't want to get into the details. So people who have worked on pins can understand this better. And mainly, I'll focus on the loss explosion in the first few iterations. So what happens is if you have not balanced the network well, and lost contributions, let's say from boundary condition, from the data, and then also the physics. If you have not balanced their contributions well, if you have not weighted them appropriately, one might blow up, the other might be really small in order, and the convergence would get affected in a way that your solutions would pretty much be junk, or you would take longer time to converge. So that's another way of looking at it. In a fixed budget, you would have junk solutions. But let's say if you have an infinite budget, then you can expect that you just let it train for a very, very long time. It will continue to train and converge to a solution in a very long time. So the loss weights also determine your convergence rate, in some sense, and also determines what you can get within a fixed budget. And then the handoff is mostly in terms of, it doesn't invoke the analysis skill automatically. So this is something that the author can specify. So this is where the human in the loop part comes in. It's not, I would say the Dhyutiman Pi is not completely autonomous. It can be if you use it in Claude Code and ask it to take a complete freehand, use all the 4 skills, do whatever you want, just ensure that it works. There are some prompts that you can just kick in and let it do these things. But I would say that if you use it on Claude Code, then at least till these 3 skills, it's automated. The 4th skill, which is analysis and reporting, is where you can add some more details. Okay, I want to look at some additional plots. I want to look at some additional metrics. Then it adds it and then computes it on the based on the checkpoints and data that you already have, and then further then hands it off over to the analysis and reporting skill. Dhruv, how are we doing on time?
So we're definitely like, it's 5:10 right now. So I think it might be good to run through the analysis and report and then jump into the workflows. That would be exciting. And then perhaps towards the last 10 minutes, we can leave it open for questions.
Sure. Okay. And again, so here is where it takes inputs. The analysis and report is pretty much wholesome because it doesn't only depend on the outputs of the scaffold and the experiments, but also looks at the outputs and artifacts of previous runs and previous skills as well, right? Like in the pipeline, which is like problem spec, then the training log verification, or any plots that are also out there. And so the plots can be a bit tricky. Sometimes if you're using a very low quality model, which is not so good at vision understanding, then the reasoning that you might get out of this can be bad. However, if you have any sort of numbers, you add some more context to it, it's still better. JSON, which is verbal, is better. But a problem spec, it understands reasonably well. So, but when you work with images or videos, it can get tricky, especially if you're not using a model. And then the report is pretty much like a reviewer document. So it talks about, okay, it's a mix of a reviewer document and an analysis report. And what is your failure mode audit? And what went wrong? What could have gone wrong? What has been implemented in a way that it shouldn't be, and so on, right? So these things have also been baked in. And what are some of the limitations? So this is again the reviewer part kicks in. How do I think as a reviewer? Say that, okay, we have done these analysis. It's often the reviewer too who puts you to trouble and ask you such difficult questions. And we want the agent also to retrospect and ask such questions to itself, so you can do a corrective loop. And then what are the recommended next steps? So this again becomes important. So this is where it helps you iterate. So since research itself is an iterative process, you fail, you learn from it, you have negative results, you have positive results. What do you learn from each of them? Then try and reinforce or modify your hypothesis, change your problem framing a bit more, and then maybe look at different candidate functions or candidate models, and then rerun. So the recommended next steps helps you to again start from maybe literature survey, or it can again go back into problem specification itself, or you go back into print scaffolding and change there. So you can get into, again, use this as an entry point to another skill. And this would serve as a knowledge base for your next iteration. And it had one caveat I would always mention here is that currently I have not implemented it in a way that it maintains session logs. So another immediate implementation or extension would be to ensure that every run of this pipeline of Dhyutiman Pi gets logged in a session as a session. And then that has a markdown compressed report in itself, which serves as a knowledge base for the next run of Dhyuti Pi. So it's pretty much like a lab notebook or lab record for Dhyuti Pi. Of course, the analysis.md also helps, but beyond that, some meta level thinking process, thought process that has gone into these hypotheses also needs to be captured. Right, so then there's failure mode audit, which is very specific to pins again. And what I would say is, if you want to adapt it to your respective domains, the sections can be retained. Just ensure that the right taxonomies and right terminologies kick in. And if you have that domain expertise, look for what often goes wrong. What are the typical gaps that are missed, even by human researchers? What is not done? And so ensure that you bake all those into various skills here. So you can always transfer the section headings or the layout of this skills to your respective domains. So this is how an example is, and then you compare across multiple runs. Again, anti-patterns. So anti-patterns is what tells you what to avoid, which is very important in my opinion. So I have covered all the skills here. So now let's probably look at one of the work examples. So these are more details, is what I explained, but so these are the typical failure modes I would like to avoid and expect that the framework refuses to compromise on. One is query expansion and multi-access synonymous literature deep dive, falsifiable, verifiable hypothesis, no exceptions, no hypothesis should be framed in a vague manner, and reference solution becomes mandatory, otherwise there's no way to tell whether pins are performing well. And analysis is adversarial by design, so that you know that the report that comes out is like from the standpoint of being extremely objective and like a reviewer of your own work. Now here's an example of 2D steady state heat conduction, because this is relatively easier. And so all you have is a square domain of unit length, and then you have a governing equation, which is nothing but the diffusion or the Laplacian equation, PD. And then you have a Dirichlet boundary condition, homogeneous boundary condition. Then you have an exact solution for this, which is very simple. Again, you can also choose a source term, and I can even set this to 0. At least for the example that I considered first, I set this to 0. So I'll just show how this goes on in Claude Code. So I just uploaded the skills to it, gave access to the code base, and said, okay, use these Dhyuti Pi skills to scaffold a pin project. I want to solve the 2D heat conduction problem. I have a Conda environment that I'd already set up. So, and use that particular Conda environment to test it out, right? So I checked the memory for project context first. And so I didn't do literature survey here. So although it says Dhyuti Pi skills, it didn't do the literature survey, and I used Sonnet 4.6. I'll show an example where it uses it, and there's a clear difference in the way it performs, and also the model was Opus 4.7. And so it creates a problem specification, which I felt was very interesting. It was like the baseline problem statement that you would do if you had probably no knowledge of what has been the latest literature out there and what is the baseline. So to answer you, Sachin, I think the problem gets specified by the skills. So it's not specified in the skills itself. The skills is structured in a way that the model ends up specifying a problem depending on the user intent. So I can go and say, I want to solve Navier-Stokes equation, or I want to solve electromagnetic equation, or I want to solve nonlinear dynamics. I want to solve climate. I can give any of these as my input. And the problem spec skill is expected to frame that problem in a way that is verifiable or has hypothesis which is falsifiable, then has clear framing of the governing equations, all the additional data and more constraints, and it has mandatory reference solutions to verify the predictions of the models against. So the skill does the job. It's not that we give the problem specification to the skill in itself, right? So now, this is where it defines the problem statement, gives a very brief abstract of it, and then gives out the governing equations. As I said, I wanted to look at since I mentioned 2D heat conduction problem, it looked at a very simplistic case where it didn't take any source of heat, source or sink of heat. It just looked at, okay, there's some temperature at some boundary, or even if it is zero, what could the solution be? What could the homogeneous boundary condition look like? So it took the simplest case. Then domain and initial boundary conditions specified, and the reference ground truth, which is my reference solution. And then you have the architecture and training plan, the architecture, MLP, simple MLP, fully connected neural network. You have the depth and width defined, what activation function to choose. Of course, literature has better, if you would have done literature survey, you get better activation functions and probably even better architecture variants as well. The sampling was very simple, Latin hypercube sampling, or uniform random based. Ablation varied across different number of sample points and so on. Then the loss was the important part. It was smart enough to figure out that I can't have unit weighted loss components. They need to be weighted in a balanced way. And it chose higher weight for the boundary losses, which is where you often see violation. And you use the optimizer. And what are my hypotheses? So this is, cool. So this is where I just wanted to pause on the hypothesis. So, right, so the falsifiable hypothesis is here. So when I say baseline convergence, it means I want the pin trained with, let's say, some baseline set of conditions, have a particular error rate and on a particular grid. And only after this passes, I know that H1 is satisfied or not satisfied. Then I have ticks or cross marks on all of this, right? I measure, everything is measurable. Every outcome of my experiment under each of these hypotheses is measurable. And I have success criteria in terms of what my errors should look like, what are the metrics that I need to look at. And so this is something that people often miss, which is physics residual or the boundary residual. So how do I even capture that? And there's also another important part about success criteria is compute time. So can I comment something about it? So I just say that, okay, training completes within 5 minutes on my Apple MPS. Great. If it doesn't, then we will know why. Right? So known failure modes, which is again based on its prior knowledge, not technically based on its literature survey. Then what's out of scope? So this helps the code be very constrained. So it doesn't move out of scope. It doesn't randomly create functions which are arbitrarily parametric and work at things to over things, right? So you don't want it to overthink within a specific guardrails. Yeah, so Path, I think when you don't have a reference analytical solution, I think the mandatory, when I say mandatory reference solution, I mean to say that you have the solution either in terms of simulations or observations or in terms of analytical solution. So if you have anything to compare against, then think about yourself as a researcher who's trying to develop pins. How else would you know that a model that you develop will work for a particular problem statement? Unless and until you have a reference, until you have benchmarks against which you compare. So think of the mandatory reference solutions as benchmarks that you would require in a particular domain to even build pin models that are valid. For example, even FDM solver works. FEM solver works. Right, so this is one. And then you have the problem spec. Then after this problem spec, it generates various artifacts. It has generated runs under each of these hypotheses one by one, serially. It didn't do all 4 hypotheses simultaneously. It did each one of them sequentially. Forget about the debugging part here, but here's where it generates the output, then consolidates all of them. Into an analysis report here. So there were some, so the bugs which I said can ignore are 2 things. One is the naming convention of your checkpoints. So if you want checkpoints for each and every run saved at multiple intervals, that's something that you need to let the model or bake into the model or into your prompt when running these. And the other aspect was mostly cosmetic side of things, right? Like how do you ensure that the report that it generates has the right presentation and so on. Yeah, so here is an analysis and report. It looks at all the runs that have been carried out. So one was based on different hypotheses that were framed. And It looks at each of these hypothesis variants, what were the thresholds that were set, what was measured, what was not measured. And so it says that anything that cannot be measured, the verdict is inconclusive. And even here, hypothesis 2 was LBGS, LBFGS reduces further by 5x, but the end loss for a particular case was not comparable, so it was again inconclusive. Then what was... so they were, interestingly, a lot of these were not, it was not able to measure. It was inconclusive. Only one hypothesis was refuted, simply based on what the table of results gave. So this was like how many iterations were used, what was the total loss, PDE loss, BC loss, PD ratio. And so this is what is helpful, because you can make very clear decisions. Okay, if this is not the case, what do I do next? Then it does some error analysis, and it comes back to your recommended next steps. Okay, save add only checkpoint, then look at LBFGS based checkpoint, repeat certain sampling to know whether it's just a single run artifact or you do it multiple seeds, and then you actually see a monotonic trend or not, and what kind of decays you could use, add Fourier inputs at feature, and so on. Right? So it gives you immediate next steps based on what it was not able to conclude on, which is very helpful, which is typically how you would proceed on carrying out next experiments to further validate the hypothesis.
Rahul, I think there's a great question. I think we can now wrap up and like sort of take questions, perhaps, considering there's just 7 minutes. Right. I think there's one from Malayaja who's talking about like what has your experience been in using these skills, especially when you're still sort of, let's say, developing domain matter expertise. Right. Like, have you sort of found it to be helpful?
Like, are you talking about case where I don't have domain expertise and I want to develop it?
It's yeah. Like, what has been your experience in developing subject matter expertise in a topic when you use this framework workflow to solve a problem?
Okay. So I wouldn't go to the extent of solving a problem when I don't have domain matter expertise, unless I know I'm able to frame, or I'm able to make some judgment about the framing being appropriate enough. Right? So at least I would possibly initially stop at post-problem specification. That's just because I'm a bit skeptical in nature. So you have literature survey, which helps you assimilate knowledge, which can help you learn and build the domain matter expertise. And then you also look at problem framing, and then you can iterate on this loop itself for a while, saying, okay, this is where I would like to understand some point better, some of this better, some of this better. Why do we design an experiment like this? Why is this hypothesis? So probing more and more, I think that helps. And if you think that, again, is quite manual, you can add another clause saying that let's do this iterative, and you give me a final 2-page executive summary, and then you also link it to a complete knowledge base, which I can link to, right? So these are ways in which you can make it work. But implementation, experimentation can happen if you feel that, okay, maybe I should break something to learn it better. If that's a viewpoint, that's also fine. But if you're trying to build domain matter expertise, at least in research, I would suggest you at least loop on step 1 and step 2 a bit for some amount of time, then go to step 3. That's again my opinion, but there are people who would also like to implement fast. Okay, there is something that I've understood vaguely. Let's implement, see what happens. So whichever works, but I would always align with the case where you do literature survey, do the problem specification, hypothesis, DOE exercise a few times first. And you can use it as a learning buddy as well. So,
thanks, Rahul. I think there's another one from Mohit, which is like sort of domain specific about, is it able to solve nonlinear equations because it needs heavy number of epochs to reach the result?
Yeah. So let me reiterate that this is a framework to orchestrate pin research, right? So this has so given that we know Sonnet or Gemini or GPT or Opus, all of them are quite smart enough to at least get to a good level of code if you give very clear specifications. I think you have enough literature, which is what you need to mine from and implement these models. the convergence time it takes to train the model is completely independent of this. So of course you can have it as a hypothesis. Okay, see what method brings the convergence faster. But to answer your question, yes, it can solve nonlinear equations as well, because it's equation agnostic. The entire framework is equation agnostic, or how do I put it? PD agnostic. The framework here is Dhyuti Pi is PD agnostic. That's what I would like to say. I'm not able to see the chat, so just
okay, yeah. I think so one, Lavanya wanted to know how much human input was required in this project, right? And I think the other one question that I think both of you can take both of them together is from David Ree, who's saying if it's helpful to, let's say, have objective tests within each of these skills. For example, like looking at the output of the literature review agent and seeing if the time that it's cited from is within a certain range. So human input and sort of, though we already have the anti-patterns to test for in the operation, what do you think about, let's say, adding a verifiability check to each skill almost?
Agreed. Okay, that's a very good point. And at least currently in the framework, I think we have, we don't have a unit test per se for these for specific skills. And I think that would be a very important next step to even check, okay, this is what it should be, right? So let's say I were to say I have papers, take papers from 2014 to 2016, and then see if it's able to reason out and get me the solution and reproduce a paper or assimilate information and give out, let's say if it comes out with some open problems, also suggest what could be the possible remedies for these. And there are multiple ways in which we could test each of these skills. And yeah, I think that would be an immediate next step. Like currently the way it is the verification is on the entire loop. So starting with literature survey all the way until analysis and reporting, then it knows whether the hypothesis is broken or not. Like, but after every run, there is some logging, there's some analysis, and that kind of updates your belief or hypothesis.
And I think I must note, like in that sense, right, like, and even to Sachin's further question, right, which is like, he's asking if you have a problem, how do you ensure that the problem statement is concretely defined enough so that the model does not go off, right? So, I mean, I think this is where sort of the human in the loop comes handy, right? Like, so like Rahul earlier said, like we were discussing, we would say that maybe these skills are good enough for about 65% automation in the workflow, right? But the remaining 35 is sort of the key handoff moments across skills where you are supposed to sort of give in your input. And I think, Sachin, to add more context on that, the fact that the problem spec skill that Rahul has constructed is so well detailed and like it sort of outputs each of those things, it makes the sort of review easier, right? Like, so you as the human being can trust the model enough because the output is structured in the way that you would want it to be, and also give more specific feedback to the model and hence just ground the entire problem a little bit more. That's great. Sorry, so Rahul, I think we're like 1 minute away, right? Like, I mean, I'd love to, like, we can continue to chat if folks want to stay behind, right? But I would love to sort of, let's say, wrap up the session by just talking about Dhyuti a bit and like also talking about CISC. Do you want to quickly talk about these two problems? So folks, for whoever joined later, like I started, right, we're doing a conference at Lost Fund called Conference for AI Scientists, where we're hoping to pull through and really probe how far these systems can do in actually doing scientific research, right? And it's open to any kind of submission. It can be like sort of fully autonomous. It can be using skills such as the ones that Rahul spoke about, or specifically the ones that Rahul spoke about. It could be like sort of auto research, which we have a session for next week, or it could be a more custom Claude Code setup that Paris next week we'll talk about as well, right? So it could be any degree of autonomy, right? But the goal is to probe how far LLMs can go. And Rahul, of course, has been kind enough to share the skills with us, etc. So if you're somebody who's a pin enthusiast, please use these skills and it should make your life very simple. But to add on top of that, he's been kind enough to also share two problems. So for anyone who wants to really also check how far these systems can go and submit to the conference and potentially win $15,000 of awards, right, they can sort of at least start attempting these two problem statements. So yeah, Rahul, do you want to walk us through these?
Yeah, so these are some of the open problems that I feel you could try and solve using the Dhyuti. At least problem 1 has verifiable solutions. Problem 2, not so much, so which is pretty much open-ended. And so given that there are 2 tracks even in CAIC in terms of verifiable and the open-ended problems, I think you can take one of them to each of these tracks. And the problem 1 is basically, how can I rapidly solve 2D Navier-Stokes equation? Thanks, Sachin, for asking that question. So I think it was leading to this. And mostly, I'm interested in external flows, plus largely deforming bodies, which is pretty much part of my thesis work as well. And how do you solve these equations? Instead of using some data, then carrying out inference and building surrogate models, can you actually use pins to solve these 2D unsteady Navier-Stokes equation, which is complex, nonlinear, has a lot of spatiotemporal scales, which is very rich in spectra and so on. And then you have inverse problems like 3D flow reconstruction from 2D planar flows. What if you have only 2D planar cross sections, and could you reconstruct the entire 3D flow, which has been attempted in literature to some extent, but it would be nice to see if you could transfer that knowledge to 3D unsteady flows as well. And if you folks are interested, do fill out this interest form, and you can get in touch and we could discuss, take it forward if need be. And finally, I would like to thank the organizers for this session. And if you want to reach out, you can reach out to our email, or you could fill this another form to join our community. And the slides are anyway updated on the repo, so you can access that from the docs folder. And this is our website, dhyutifrontiers.info, where anything that we do gets hosted there. And you could see that the conference repo, the slides, even a cohort that we have been running very closely on scientific computing and scientific machine learning is also posted on the website. And any questions, discussion, and feedback are welcome. Please let me know. Very happy to answer.